Recently, we've learned a lot of rules to help us compute derivatives, including power, product, quotient, and chain rule. And today we're going to learn not so much a rule, but a process called implicit differentiation. So our learning target is to compute derivatives using implicit differentiation. So a good place to start is defining what implicit means as far as a function. All the functions that you've seen in this course so far have been explicitly defined. So y is defined as a function of x. So y equals f of x equals a function, and those are the derivatives we've been practicing. In contrast, an implicitly defined function is one in which y is not defined as a function of x. So we see f of x comma y equals 0. What that means for us is that when we see the function, the x and y variables are going to be mixed up on both sides of the equations. So it's not going to be a very straightforward example like y equals 2x. So we're going to have to untangle those algebraically as well as find the derivative. Now that we have a better understanding of the difference between explicit and implicit functions, let's define implicit differentiation, which means the process of taking a derivative of an implicit function. Since y is always a function of x, then any function of y is automatically a composition, and we learned that compositions require the chain rule. So any function of y becomes a chain rule problem, so that when we are taking the derivative of a function of y, we're going to have to remember to always do the derivative of the inside function, and that y is going to be our inside function. So we're going to have to times, because the chain rule says to times or multiply by our inside derivative by this dy dx. We learned that this notation means derivative. We haven't used it a lot, but we do use it in implicit differentiation, so we'll get a little more comfortable with what it means. It's the derivative of y with respect to x. I have a list of steps here that I'd like to talk through with you, and we can refer back to them as we work out a few examples. And of course, they'll make a little more sense as we work through an example, but let's get an overview of what we're going to be doing in this process. So step one, we're going to differentiate, which is just saying to take the derivative of both sides of the equation with respect to x. So that's when we're going to start thinking about this dx denominator in our Leibniz notation, dy dx. Step two says to move terms with dy dx to one side. So we're going to see terms that have this dy dx attached to it that come from the chain rule situation we talked about already. Step three, we're going to factor out dy dx. So dy dx actually becomes a GCF. We might have more than one in the expression on one side of the equation, and so by factoring it out as a GCF, we then just have one dy dx. And that really takes us to our ultimate goal, which is to solve the dy dx. Because dy dx, remember, is the derivative, and that's what we're looking for. We're looking for the derivative of the function y. So let's go ahead and talk about these 4 steps in action. I'd like to start with a really basic example to show you what's happening with this respect to x idea. I decided to use line paper because I want to clearly explain this example, which I know looks like a very simple example, but I'd like to compare what it looks like when you solve for the derivative in prime notation, which is what we've been primarily using this year so far, versus Leibniz notation, which is what we're going to use for implicit differentiation. So if I had asked you to take the derivative of y equals x before we talked about implicit differentiation, you would have said, okay, the derivative of y is y prime. The derivative of x to the first using the power rule is 1x to the 0, or 1. So you get y prime equals 1. When you look at the derivative from the other notation perspective, or the Leibniz notation, we are thinking about taking the derivative of both sides with respect to x. So using that Leibniz notation, we're taking the derivative of y with respect to x, and I should have left myself a little more space there, the derivative, that's a d, of x, again with respect to x. So when we simplify, we see that we have dy dx, which is our notation that represents derivative. And on the right side, despite my bad handwriting, hopefully you can see that we have dx over dx, and any expression divided by itself simplifies to 1. So we indeed did get the same derivative, we just thought about it from different perspectives as far as notation. And I show this really simple example because a lot of students ask me, well, why do we do dy dx and not dx dx? And we do, but we're from here on out going to understand and assume correctly that dx over dx always gives me 1. So we just don't take the time or effort to write dx dx every time we take the derivative of x with respect to x. Our second example is a little more complicated because we've got some coefficients and some exponents. So let's take a look at this one. We have 4y cubed equals 5x squared. We're going to take the derivative of both sides with respect to x. And so when I see a y function, I have to understand that any function of y is a composition because it's a function of x. And I'm going to have to do chain rule. So for purposes of learning and taking our notes today, I'm actually going to put parentheses around the y to remind myself that this is an outside-inside chain rule situation. I don't need to do it for the x, but I will just for illustrative purposes so that you can see once again we're going to have that dx over dx cancel out. So once I recognize that this is a chain rule problem, I do my outside derivative first. It is a power. So the power comes down, multiplies my coefficient 4, it gives me 12. I copy my inside function. Power rule says subtract 1, so I get 12y squared. And then chain rule says multiply that by the inside derivative. Well, my inside function is y, and the derivative of y with respect to x is always dy dx. So basically, anytime you take a derivative of a function that has y, you're always going to get this times dy dx as part of the chain rule. The right side is very similar to the left, although we have the variable x instead of y, so let's see what happens. The power rule gives us 10x to the first. The inside derivative of x with respect to x again gives us that dx over dx, which we will cancel to 1. So this is the last example that I'm going to show that the x inside derivative always cancel to 1. So let's go ahead and finish solving for dy dx. So I just cleaned up all of my derivatives here. I got 12y squared times that dy dx equals 10x. Remember that was times 1. So to solve or to get dy dx by itself, algebraically, I would have to divide by 12y squared on both sides. So final answer, when I divide by that 12y squared, my dy dx, which is my derivative that I was looking for, reduced the 10 over 12 to 5x over 6y squared. When I first look at our third example, I see right away that we have x times y, and that's going to be a product because x and y are separate functions, so we have to use our product rule. So we're going to take the derivative of both sides with respect to x. So just to tackle my product rule first, I would copy my left function. My derivative of the right function y is always dy dx, since we're doing it with respect to x, plus for product, the right function is y times the derivative of the left, which is 1. And remember, that's actually dx over dx, but we agreed that that would always simplify to 1. After my product, I had to take the derivative of minus 3x squared. So applying the power rule, that gives me minus 6x to the first. And on the right side of the equation, the derivative of y with respect to x is always dy dx. So basically, whenever you take the derivative of y, you will get a dy dx. And you'll take the derivative of x normally, because that dx over dx is always 1. Step 2 says to move any terms with dy dx to one side. Since I already have the dy dx over on the right, I'm going to move this term, notice it is attached to an x, to the right side by subtracting, since it's a positive term. We now have y minus 6x equals dy dx minus x times dy dx. Step 3, we're going to factor out the dy dx. When you factor dy dx out of itself, you're left with a 1 minus, factored out of that term leaves you with an x. Finally, our last step, solve for dy dx. I'd have to divide by that quantity 1 minus x, and here's our final answer.